Hey everyone, I'm Chirag, and today I'm going to talk about Amazon S3 vector buckets. So, Amazon S3 just got a major upgrade, that is S3 vector buckets, which brings the native similarity search right within your storage layer. Imagine if your regular S3 bucket could handle advanced, context aware use cases like personalization, product recommendations, image deduplication, and more, all without spinning up a separate vector database. With S3 vector buckets, which is in preview, you can store, index, and query vector embeddings directly inside S3. That means you can power similarity search for AI driven applications right from your storage layer. Traditionally, building this kind of similarity search involves a lot of extra infrastructure like vector databases, data pipelines, indexing logic, scaling consideration, and more. It's basically a heavy lift even before you have shipped your first prototype. But now, S3 vector buckets change the game by bringing native similarity search right into your S3 storage. Let's first understand what is vector and why it matters at the very high level. So, what exactly is a vector and why is it so powerful for search? In AI, a vector is just a list of numbers, but behind those numbers, there is a meaning. And that is how we convert complex inputs like images, text, or user behavior into a format that machines can work with. So when two products are similar, their vectors are close together in the vector space. That's the core idea. The closer the vectors, the more alike the items are. Instead of matching exact words or pixels, we just compute the distance between vectors. The smaller the distance, the more similar they are. And this concept powers everything from recommendation systems to visual search to smart assistants. In the hands-on section, we will build a fashion product search system using S3 vector buckets, which will be powered by both image and text-based queries. The dataset that we are going to use here is fashion product images dataset, which you can download from Kaggle. It has around 44,000 products from multiple categories. And as a part of this dataset, we have images, we have styles directory, which has the JSON file. It contains the metadata information about the product. And then we have images.csv and styles.csv. So as a part of this hands-on, we are only interested in images and the two CSV files, that is images.csv and styles.csv. So images.csv contains the file name and the image link, and styles.csv contains metadata information about the respective product. So go ahead and download the dataset from here. I have already downloaded the dataset and placed it in my data directory. As a next step, let's go through the steps that we will implement as a part of our hands-on from start to finish. The first step is resource creation. We will start by creating the S3 vector bucket, and this vector bucket will enable us to store, index, and search vector embeddings directly from this bucket. And this does not require a separate vector database. Now, once the S3 vector bucket is created, we are going to create two indexes within that vector bucket. The first index would be the image index, and the second index would be the text index. So image index is for storing embeddings generated from product images, and text index is for storing embeddings generated from the product names. And these indexes will be the foundation of our similarity search. The next step would be the data to vector indexing pipeline. Now in this step, we will prepare our fashion dataset, which contains both product images and product names. So as a step one, we will start with our fashion data, splitting it into two parallel streams. That is one stream for product images and second stream for product names. As a step two, we will use Google's Vision Transformer model to transform each image into a vector representation. And similarly for text, we will use Sentence Transformers model to transform each product name into a vector. Now, once we have all the respective vectors from images and text, we are going to batch those vectors and we are going to upload those vectors into the indexes that we have created within the vector bucket. So for images or the images vectors, we are going to upload those vectors into the image index. And for text, we are going to upload the text vectors into the text index. Now at this point, our S3 vector bucket is fully populated with embeddings and ready to be queried. So the step 3 is querying and result fusion. Now once the indexes are ready, we can start querying. So if we put the product image as our query, it will be matched against the image index to return the top k-similar results. That is top 10 matches or top 20 matches, whatever number that you mention in the query. Similarly, if your input is a text like product name, then it will be matched against the text index to return its top k or top 10 similar results. And then if we want, we can also combine the strengths of both searches. That means we can take the results from image query and the text query and then fuse them using something like reciprocal rank fusion and return or show the combined results. So that is basically the result fusion part of it. So these are the 3 steps that we are going to follow or implement as a part of this hands-on. Okay, so let's start with the creation of the Amazon S3 vector bucket. So to create the S3 vector bucket, you can log into your AWS management console and navigate to Amazon S3 service, and then click on the vector buckets from the left panel, and then click on create vector bucket from the top right corner, provide the name of the bucket, and then simply click on create vector bucket. Another way to create the S3 vector bucket is via AWS CLI. So we will create this S3 vector bucket using AWS CLI. So let's go to the terminal, and I'm going to copy a command from my blog to create the S3 vector bucket, that is AWS S3 vectors, create vector bucket followed by the bucket name. So let's copy and paste. Make sure you have the latest AWS CLI version, because S3 vectors is something that was recently introduced, and AWS CLI does not have the support for S3 vectors in the previous version. So make sure you upgrade your AWS CLI. So I'm going to modify this vector bucket name to media1 vector bucket. It could be anything. And just press enter. It typically returns this kind of output that says unknown output type clear, but that means it has already created the vector bucket. We can check into the AWS management console. So let's go to the console, click on vector buckets, and as you can see, media1 vector bucket is created. Okay, now since we have created the S3 vector bucket, we are going to create 2 vector indexes within this bucket. One is image index and another is text index. So again, you can use the AWS management console to create the vector index, or you can also use the CLI commands. You can copy and paste the commands from my blog. So over here, we have the command from the image index, and you can also use Boto3 if you like. And here we have the command for creating the text index. So what we will do, we will create the image index using AWS CLI, and then we will create the text index using AWS management console. So let's copy and paste this command in the CLI. So what this command is saying, AWS S3 vectors, create the index where we want to create the index. So that would be your vector bucket name. So in my case, it's going to be media1 vector bucket. So let me modify this. And then you provide the name of the index. So in my case, I'm providing img-index. And then you provide the data type of the vectors. Right, so that is going to be the float 32. So currently it only supports float 32. And the size of the dimension. So in my case, the dimension of the vector would be 768, and then you specify the distance metric, that is cosine. Why we are specifically saying the dimension as 768, it's because the model that we will use to transform the product image into a vector outputs a 768 dimensional vector. So that is why we are mentioning 768 as a dimension. Okay, and then press enter. So again, you will see something like unknown output type, colon clear, but it typically means that the index is created, as you can see over here, that is the image index. So now we will create the text index. So simply click on create vector index, provide the name. I will simply say txt-index. And again, we need to specify the dimension value, right? So that is going to be 384 for the text index. And then the distance metric would be cosine. Additionally, you can add the non-filterable metadata over here. But I'm not going to do that as a part of this video. That is optional as well. So once you have this configuration in place, click on create vector index. So now we have successfully created the image index and the text index. And again, we mentioned 384 as a dimensional value or the embedding size while creating the text index. It's because the model that we will use to transform the product name into a vector outputs a 384 dimensional embedding size. So that is the reason that we have used 384 for text index and 768 for the image index. And if you notice, then we used cosine similarity as a metric for both the indexes to retrieve the similar results or the similar matches. It's because cosine similarity compares the angle between vectors, which is a kind of a great way to measure how semantically similar the two vectors are, especially when we are using the embeddings that are normalized. So that is why we have used or selected the cosine similarity as a metric. That's our step 1, which was the resource creation. Now let's move on to the step 2 and step 3, which is the data to vector indexing pipeline and querying the indexes to retrieve top similar matches. So we will walk through both the steps in a Jupyter notebook where we will build a product search system using Amazon S3 buckets. This means we can search products by both text and images separately, and even we will look at how we can combine the results coming from the text query and the image query using something like reciprocal rank fusion. And this is all again without a separate vector database. So let's move on. First things first, if you would like to follow along, start by cloning this repository, which you can see on my screen. And this link is also available in the video description. The only prerequisite is installing the UV package manager. And once that is installed, you can simply run UV sync command to install all the dependencies needed for this demo. So let's run that command. I have already pre-installed all the dependencies using UV, so that is why it didn't took much time. And UV is quite fast as well as compared to the pip. So once you have executed UV sync command, all you need to do is you need to run UV run Python Jupyter Lab to run the Jupyter notebook. Oops, it's UV run Jupyter Lab. It's not UV run Python Jupyter Lab. So let me copy and paste the link from here itself in the browser. So here we are. Let me zoom in a little bit so that it's readable. Okay, so let's go ahead and open our Jupyter notebook. It's within the notebook directory. So now I'm going to give you a walkthrough of this Jupyter notebook. We will go through it step by step, looking at how the data is prepared, how we generate embeddings, how we upload them into the S3 vector bucket, and finally how we query and visualize the results. So by the end of this walkthrough, you will have a clear picture of the entire workflow in action. But before we jump into the walkthrough, make sure you have downloaded the fashion dataset and placed it within the data directory. Something like this. And there's one more configuration step that we need to do is to create .env file. So I have already created that file. Let me open that. So within this env file, we are simply defining the resource name that we have created as a part of the resource creation step. That is the vector bucket name, image index name, and the text index name. So if you don't have .env file, just create one and define these key value pairs. And don't worry about the storage bucket name. I'm only using it here as the product images storage reference for S3 URI so that I can have that S3 URI as a part of the metadata. And this is totally optional. So once you have this .env file, let's go back to the Jupyter notebook. The first step that I'm going to do is restart the kernel and clear all the outputs. Now we will go through this notebook step by step, or I would say cell by cell. Okay, so first we are importing all our libraries and the dependencies that we will need for data handling, image processing, accessing AWS services, and embedding models. And we also load our environment variables using .env. So that's our first cell. Next we are defining a random seed so that we can have the reproducible results. Next, we are defining our Boto3 client for S3 vectors to access the S3 vector bucket service, to upload our vectors to the respective indexes and then query those indexes and so on. Next, we are defining our base data path, and this is nothing but the reference to the fashion dataset that we have downloaded. And then we are loading the vector bucket name, image index name, and text index name from .env file or the environment variables. So let's run this. In the next cell, we are loading the respective models to transform our raw inputs into the respective vector representation so that we can upload those vector representation into the respective indexes. So for images, we are using Google Vision Transformer model, and for product names, we are using Mini LM L6V2 from Sentence Transformers. And I had also mentioned this earlier that Google Vision Transformer model will output the vector size of 768, and this Mini LM Sentence Transformer model will output 384 dimensional vector. So here we are simply loading those models. Now in the next 4 cells, we will load 2 CSV files, that is images.csv and styles.csv. So if I open this fashion dataset, then we have this images.csv and styles.csv. So that is something we are loading over here. And images.csv contains the file name and the image link, and styles.csv contains the metadata information of the respective products. And then once we load the CSV, we are merging them together, removing any invalid records, and then we are sampling 10,000 products for the purpose of this demo that is over here. Right, and then each product will also get an S3 URI so that we can reference it later, and this is totally optional again. So let's run this 4 cells. So now we have 10,000 products or 10,000 records loaded into our sampled data frame. Next, we have the helper function, that is get embeddings. So this helper function will simply transform the raw inputs into the vector representation using the respective models. So this function takes in either raw images or the text as an input along with the mode flag and convert them into the vector representation using the respective models. So if the mode is image, we will first pass on those raw image input to the image processor, and whatever output that we get from the processor, we will pass that output into the model, right? And then we extract the CLS token, we normalize it so that the vector has the unit length, and return that output as a list. And if the mode is set to text, we use the text model to directly generate embeddings and then return those as list as well. So in short, this function transforms both images and text into comparable L2 normalized vectors, which makes them ready for similarity search or indexing in our pipeline. So that's get embeddings. Let's run this. Next, we have the helper function, that is display results. So this function will visually represent the search output. So when we will query the index, we will get some output, and display results is something that we will use to display that output. So as a part of the output on the left, you will see the query itself, and it could be either an image or the query text. And on the right, we will show the top matching products for that particular query. And for each match, we will display the product image along with its name. And depending on the mode, we will either show the similarity distance or the RRF score. So that's display results. Next, we have the create and upload vectors helper function. So this function takes our data set and process it in batches of 500. So for each batch, it generates the embeddings using the helper function get embeddings that we have defined earlier. So for image part, it pass on the raw image input, right, with the mode as image. And for the text part, it passes the raw text input with the mode as text. And then this get embeddings function will return the list of list as an embeddings or the vector representation of whatever input that we are passing over here. So once we have the embeddings, each product or each embedding gets paired with their respective metadata, that is gender, category, type, season, product name, and optional S3 URI. And we do it for both text vectors and the image vectors that you can see over here. And finally, the function uploads both the image vectors and the text vectors into our S3 vector bucket using the put vectors API. So that is our create and upload vectors helper function. So let's run this. Next, we have the query S3 vectors helper function. So this helper function sends a query vector that is over here, which we will receive as a part of the parameter, right? So this function will send this query vector to a specific index. So if it is the text input, then it will query the text index. And if it is the image input, then it's going to query the image index. So that is something, again, will come as a part of the parameter. Okay, so this is going to query the respective index, and the response that we will receive will be the top k matches, and k will be defined again as a part of the parameter. So if you want top 10 matches, then you define k as 10. Okay, maximum you can define up to 30. So this function in general is going to return the matches for the given query, that is the top k matches. So that is our query s3 vectors helper function. Now next we have the RRF merge helper function. This is our last helper function. So this function takes the results from both image search and the text search and merges both the results together using reciprocal rank fusion. Okay, so what this means is results that rank highly in either list gets higher combined score. So the strongest matches naturally rise on the top. So this will simply merge both the results using RRF, and then it will return the fused result set as a part of this function. So that's our RRF underscore merge. Now we are going to execute the whole workflow. So the first step is to create and upload the vectors within the respective indexes. So we now run our upload function, batching through the sampled underscore df, and then this will also store the embeddings into the respective indexes. So let's run this. So this is going to take around 7 to 8 minutes. So let's wait. So it took around 8 minutes 43 seconds to prepare the vectors from the raw input for both images and text for 10,000 records, and then to push those vectors into the respective indexes. Now next, let's run a query using both text and image. So this is going to be our test part. So for the text side, we will search with the phrase saying men's green polo t-shirt. And for the image side, we will use a sample t-shirt image from the test set that I have. And then we will generate embeddings for both inputs and query the indexes. So let's run this, and let's run this as well. So the text embedding is queried against the text index that is defined over here. We should be using the variable that we have defined above instead of hard coding it. I will replace that. I'll simply say text index name. And for the image part, the index that we will be querying is image index. Okay, so let's rerun this. The k that we have defined is 10, so we want to retrieve top 10 matches for each of the query. And next we are going to visualize the results. So first we will display the image based matches. So let's run this. So on the left, we have the query t-shirt image, and on the right, we have the top k matches or the top 10 matches retrieved from the image index. And similarly, we are also going to visualize the text-based results. So on the left, you can see that query text was men's green polo t-shirt, and on the right, we have top 10 matches for this particular query from the text index. And finally, we will try reciprocal rank fusion or the RRF. So here we will take the top results from both our image search and the text search, and then we will merge them and calculate a fused ranking score. So this way, products that scored well in either search mode will rise to the top in the combined output or the combined list. So let's run this. And one thing to note here is that S3 vector buckets currently do not natively support merging multi-model results. So that is why we are using something like RRF to merge the results from different modalities. And then let's use our display results function to visualize the fused results side by side with the query text and the image along with their RRF scores. So let's run this. So here, as you can see, here is our query image and here is our query text. And then these are the fused results with the RRF score that is 0.0164 and so on. Now, apart from this, I have also built a simple Gradio UI that is very easy to use. So let's go back to the Visual Studio Code and let me open a new terminal. And all the configuration and everything is defined within this app.py that you can get it from the repository. So all you need to do is you need to run uv run python app.py. And we can copy this URL and go back to the browser. Open a new tab and paste it over here. So this is how the very minimalistic UI looks like. So here we have search mode, that is text, image, and both. So based on the search that you want to do, you can select the respective mode. So let's say for text, I will say men's polo t-shirt and click on search. So this is going to display the respective results, and same for image. So click on image, upload or drop the image over here. Let me do that. Let's say upload. I'll say t-shirt, and then I will click on search. And here are the results. And if you want to search using both, that is, you want to combine the image search results and the text search results using reciprocal rank fusion, then select both as a search mode and click on search. So here you will see the product name and the RRF score, and here are the results. And if you want to try this yourself, the link to all the resources, the notebook, the UI code, and the setup instruction, everything is in the video description. Let's now dive into some practical considerations, things like performance, cost, accuracy, and overall design. So the first is performance considerations. So S3 vector buckets are pretty quick. Queries usually come back in under a second, often well below 1000 milliseconds. And that's fast enough for most interactive applications. But keep in mind, latency does go up as your dataset grows, or if you are working with really high dimensional vectors. So both the number of vectors and the dimensionality play a role in performance. The next is storage and cost considerations. Higher dimensional vectors don't just affect performance, they also take up more storage, which means higher cost. And the good news is an index can scale up to 50 million vectors, and that's huge. But you will want to keep an eye on dimensionality to make sure you are not overspending. Next is recall and accuracy considerations. So accuracy depends a lot on the embedding model you choose, the size of your data set, and the diversity of your incoming queries. So generally, the better the embeddings and the more representative your data set is, the better your recall will be. So choosing the right model for your domain is a key. Next is design considerations. So S3 vector buckets are great for workloads where you don't need millisecond level real-time results. It is well suited for things like batch jobs or periodic searches that comes in. But a couple of caveats that you need to be aware of is you can't partially update a vector or its metadata. If something changes, you need to re-upload the whole entry within the index. There's also no built-in multimodal search. So if you want to combine text and image results, you will need to have your own approach on the client side, something like RRF that we saw in the hands-on part. And on the plus side, it is fully managed. So you can just start storing and querying vectors right away. No extra infrastructure is needed beforehand. Where does S3 vector buckets really shine? They are great fit if you want to experiment with vector search quickly, if sub-second query latency is good enough, and for use cases like product recommendation, visual search, or content discovery. They might not be the best fit for real-time systems or use cases where you are constantly updating vectors. But if scalability, cost efficiency, and ease of integration are high on your list, S3 vector buckets hit the sweet spot. Thank you so much for following along. And if you want to explore the code, the dataset, and the UI that we built in this hands-on, then all the links are in the video description. Until next time, happy building.